I'm going to talk about verification of two data part designs, one multiplier and one divider, using formal sequential equivalence checking. This is based on the work we did with AMD. First, I'll talk about why we chose formal to verify these two designs. Then I will go into verification details of both designs one by one. Both designs had large input sizes along with multiple modes such as signed and unsigned multiplier and divider. Large input sizes along with various modes corresponded to huge number of input scenarios, and therefore formal was preferred over simulation. For data part designs, traditional model checking is not suitable, and therefore we use sequential equivalence checking. Now I will go to details of multiplier verification. The multiplier had various input sizes, 8-bit, 16-bit, 32-bit and 64-bit. Along with that, it worked in signed and unsigned mode. We had two versions of multiplier, one earlier version called base multiplier and one modified version called final multiplier. We verified both versions. First, I will go through details of base multiplier and then details of final multiplier. We use Synopsys formal verification tool Hector. We were able to prove base multiplier using SDPS engine of tool without going into sequential equivalence checking. SDPS is a customized engine for multipliers and it does not need a reference model. Final multiplier was the modified version of base multiplier, and there were two differences between base multiplier and final multiplier. One, final multiplier was optimized for power and performance. Two, the sequence of compression of partial products was different in final multiplier compared to base multiplier. We started with HTPS with final multiplier 2, but SDPS did not kick in. Then we moved to sequential equivalence checking approach using already proven base multiplier as reference model. We started with end-to-end checkers and end-to-end checkers did not converge. Then we applied assume guarantee method to break the end-to-end sequential equivalence problem into multiple but smaller sequential equivalence problem. To apply assume guarantee method, we identified internal signals between base multiplier and final multiplier that can be proven equivalent. However, when we tried to prove them, we got failures. The reason of failures was the difference in sequence of compression of partial products between base multiplier and final multiplier. So we created another version of final multiplier with sequence of compression of partial products, same as in base multiplier. We call this version of multiplier intermediate multiplier. The plan was to prove intermediate multiplier against base multiplier and then prove final multiplier against intermediate multiplier. There were two differences between base multiplier and final multiplier, power optimization and difference in sequence of compression of partial products. However, between base multiplier and intermediate multiplier, there was only one difference, power optimization, and there was only one difference between intermediate multiplier and final multiplier, which was difference in sequence of compression of partial products. With this approach and after using assume guarantee method, we were able to prove both intermediate multiplier against base multiplier and final multiplier against intermediate multiplier. With that, we were able to verify multiplier design. Now I will go to details of divider verification. The divider also had various input sizes, 8-bit, 16-bit, 32-bit and 64-bit. Along with that, it worked in both signed and unsigned mode. Again, we used sequential equivalence checking to verify divider. Unlike multiplier, in this case we had an already proven divider as a reference model. The end-to-end proof did not converge, and then we moved to assume guarantee method just as we did with multiplier. Unlike multiplier, we did not get any failure, but proofs did not converge either. We analyzed the design for complexity and found out a set of points that were being used iteratively at different stages of division algorithm. We further analyzed COI of these points and applied cut points on them and assumed them equal. In a separate setup, we were able to prove these points equivalent. After applying cut points, we got failures for division result. The root cause of failures was the cut point taking illegal values not allowed by RTL. We added constraint to disallow the illegal values. With this, we were able to prove equivalence for division result. In a setup without cut points, we also proved that disallowed scenarios never occur in RTL. With that, we were able to verify divider. Coming to conclusion, we successfully verified one multiplier and one divider using sequential equivalence checking. Learning of this work were: one, optimizations such as power and frequency optimizations can add complexity for formal. Two, repeating formal proof after each change may converge faster. Thank you.